In this video, we are going to do an optimization question where we maximize an area. So the example says, prison cells in Azkaban are rectangular and have 3 walls with one side open to the sea. Due to a surge in prisoners, the Dementors split the prison cells into 3 smaller rooms by putting in 2 walls perpendicular to the side open to the sea. If the total base length of the walls in the new setup is 200 feet, what is the maximum possible area of the original cell? Okay, so we have this word problem, and it's an optimization question. And remember, the first thing that we do in an optimization question is identify the quantity that we are trying to optimize, that we want to maximize or minimize. And in this question, we want to maximize the area. Okay, because it says find the maximum possible area. Okay, the next step is we draw a picture. And in this problem, I think a picture is appropriate. So initially, this prison cell is rectangular. It has 3 walls, and there's one side that's open to the sea. So I'll put a dashed line there. So there's no actual wall here. This is open to the sea, but I'm just drawing a dashed line so I can complete that rectangle. Okay, and then we have this is open to the sea, so the sea is over here somewhere. But then the Dementors, so these are creatures in the world of Harry Potter, it says that they put in 2 walls that are perpendicular to the side open to the sea. Okay, so I have to put in a wall perpendicular to the side open to the sea and another wall perpendicular to that side. It doesn't say anywhere that they have to be evenly spaced. So notice I create 1 room, 2 rooms, 3 rooms now, like the problem says, 3 smaller rooms. But they don't have to be equally spaced. Okay, so I have a setup like this. And now let's assign some variables. So maybe this vertical length, I'll call this x. So that's x, that means this is x, and this is x. And then let's call this whole horizontal length y. Alrighty, so from here, we are ready to start to write down our objective equation. So our objective is an equation for the quantity that we are trying to optimize. In this problem, that's the area. So I'll write area equals, and the problem says the area of the original cell. That was the larger rectangle that we had initially, and that area is x times y. Okay, and we want to maximize this. Right now there's 2 variables on the right-hand side, and like we saw in the last video, to be able to handle that, we want to get this in terms of 1 variable. And to do that, we use another equation called the constraint, which we form based off of other information that's given to us in the problem. So the other piece of info it gives us is that the total base length of the walls in the new setup is 200 feet. So this is a picture of the cell sort of from above. This is sort of a top view. And the base length is sort of the length of each of these walls as I can see it from the top. So it's this x plus this x plus this x plus this x plus that y. That's the base length, the total base length. So if I add those together, we get 4x plus y, and that needs to be equal to 200. All right. Okay, so we have our objective, we have our constraint. Now what I'm going to do is isolate one of the variables in the constraint so I can substitute into the objective. And I can technically isolate either one, but I'm going to isolate y just because that's a little easier to isolate. Y is 200 minus 4x. And now let's substitute. Now we will substitute. So doing that, we get area equals x and then times our y value. Our y value is 200 minus 4x. All right, and now I'm going to simplify this and then take the derivative. So area equals, if I distribute x, 200x minus 4x squared. Now I have a function that's in terms of just 1 variable, and we know how to maximize and minimize things like this. We take the derivative. So here we're going to take the derivative with respect to x. When we do that, we'll get a prime. I could also write dA dx, because it's with respect to x. And that equals, so the derivative on the right is 200 minus 8x. So we will need to know when is this equal to 0 and when is it undefined. So let's set this whole derivative equal to 0. So we get 200 equals 8x. And if I divide by 8, we get x equals 25. And this whole thing, my derivative, is never undefined. Let me just write undef. It is never undefined. So now I can write down my critical numbers. So my critical numbers, we just have one. It's just x equals 25. So we now need to test to see whether our critical number corresponds to a max or corresponds to a min. Remember, in this problem, I'm trying to find a max. In the last video, we talked about 3 ways we could test our critical numbers. There was method 1, which is the closed interval method. There was method 2, which is what I'm going to do here. Method 2 was to use the first derivative test. First derivative test usually tests for local mins and local maxes. So we give a little extra justification to explain, well, why is this particular local min or this particular local max going to be an absolute min or absolute max? Okay, there was also method 3, which was to do the second derivative test plus a little justification, but I won't do that here. I'll just do method 2. Okay, so before I go to my number line, it's going to be helpful to think about the interval for my variable, just so I don't plug in things that don't make sense in the context of the problem. So for my variable x, that's the variable that we got a in terms of now. X is a length of 4 of these walls. The smallest that could be is 0. In fact, I can even say x is allowed to be equal to 0. If x equals 0, that would give us what's called a degenerate rectangle. Which is a rectangle. It's just a rectangle where one of the sides has a length of 0. Okay, and for the purpose of this question, I'm going to consider that as a valid rectangle. Okay, and what's the biggest x could be? All right, so the biggest x could be is actually 50. Because if it was 50, we'd get 50 here, 50 here, 50 here, and 50 here. And those would add up to 200, and that would make the y value be 0. And that would give us another degenerate rectangle. So the biggest x could be is 50, equal to 50. And I could even add 50 here and say, oh, x equals 0 and x equals 50. They both give me degenerate rectangles. Degenerate rectangles, let's do plural. All right, so we are now ready to make our number line. Okay, so I'll make a number line. I'm going to put the 0 and 50 here just to remind myself that I don't want to plug in anything smaller than 0 or bigger than 50, because x can't be outside of this interval. And also put a tick mark at my critical number, which is 25. And now I need to keep track of my derivative. And this derivative is simple enough. I'll just write the whole thing as it is. A prime is 200 minus 8x, and then I'll keep track of the original function. So I'll split this into rows and columns. Okay, if I plug in something smaller than 25, like 1, into this derivative, my derivative is going to be positive. But if I plug in something between 25 and 50, you could check it, but that'll make my derivative negative. Okay, so when the derivative is negative, a is going to be decreasing. The original function will decrease. When the derivative is positive, the original function is going to increase. Okay, so using the first derivative test, it would technically tell me that I have a local max at 25 because my function changes from increasing to decreasing, and it's continuous there. So I have to give a little extra justification to explain, well, why is that local max an absolute max? So recall how we do that. I say something like, since a is increasing for all values of x less than 25, and it's decreasing for all values of x that are greater than 25, that will mean that the local max at x equals 25 is also an absolute max. It is also going to be an absolute max. Graphically, if I were to draw some axes, and I put 25 here, and then I put 50, my function is increasing the whole way before 25, and it's decreasing the whole way after 25. So because of that, it can never sort of change directions and get higher than it is at the point where x is 25. Because if it were to change directions, there would have been something else in the sign chart, but there isn't. It's just increasing before 25, and it's decreasing after 25. Okay, so that is how I justify why it's an absolute max, not just a local one. And the very last thing that I need to do in these optimization questions is to answer the question. Answer what this specific question wanted. All right, so what did this question want? Did it want the dimensions of the cell, or did it want the area? If I look back to it, it said, well, what is the maximum possible area? Okay, so let's get the area. So I'm gonna use my area equation, which was this, 200x minus 4x squared, and I'll plug in the x value that gives me that max. Okay, so we'll get area equals, it was x times 200 minus 4x, and if I plug in 25, we'll get 25 times 200 minus 4 times 25. This whole thing in parentheses will be 100. And 25 times 100 is 2,500. And there are units of length here, which were feet. So for area, it's going to be feet squared. That is a maximum possible area of the original cell.